reductions. This presentation is going to focus specifically on the back-drivable type. This is just strictly because you're dealing with mechanisms that have to be inside a dynamic environment that interact with things that might collide with your actuators. Having a back-drivable system allows you to get input back through your motors through resistance and figure out exactly what your system is doing. And so that's kind of a almost like a future-proof step that you want to take with your with your system there. Once we get to the point where we're doing like physical testing of the prototype and we have it moving around and we're like walking in it, being able to get data back from our motors about like how much they need a push to keep, like if you jump off of a curb, which is probably way down the line, or if you even take a step off of a stair, being able to back drive your actuators allows you to basically get a spring effect from them. And this presentation doesn't go outside the realm of different reductions. So in the case that we choose to go for a different type of actuator outside of a radial, like rotating motor, this would not apply as directly. And then it also doesn't specifically apply to the hip. It could apply to any actuator on the exoskeleton. So factors to consider for your actuator or for your reduction rather. First is torque capacity. And so this is basically the amount of static load you can put a locked, like if you had a gear train, for example, just a simple two gears next to each other, and you locked one of them, and then you pushed as hard as you could on the other, its torque capacity would be that point at which the teeth shear and break. So torque capacity is important, and they differ from different types of like reducers, because some, like our Planetary Gearbox from last year, engage multiple teeth at the same time, compared to a standard gear train that only engage like one tooth at a single time. And so different types of like reductions can have larger torque capacities than others. And so having one with a higher torque capacity for our application would be advantageous, because we'd like to have a smaller package, because what you'd have to do for a standard gear train, for example, if you just had two teeth in contact or one tooth in contact, then you'd have to basically make those teeth larger, which is a packaging concern. Which brings me to my next bullet point, which is the packaging of the overall reducer. Different types of reductions, and you'll be able to visualize this a bit better when we get to the other slides. Different types of reductions take up a different amount of space. Like if you wanted to achieve a 10-to-1 reduction on a traditional gear train, you need one gear, which is 10 times the size of the second gear. And so basically you would have a really small gear, which is like 0.1 inches in diameter. And then you need a really big gear, which would be 1 inch in diameter. And basically scaling this up to something where you need like a 400 like gear reduction would take up a lot of space compared to something like a Planetary Gearbox that does it in a bit more of a clever way, and some other gearboxes that you can think about. Efficiency, this is to do a lot with the internal friction of your drive. I don't know how much this matters for us initially right now. Efficiency is typically something that you size for when you have a system that you're trying to have like optimize, and I don't think we've quite reached that point. Like you want your output power of your like outside of your gearbox to be similar to what was inputted, because that saves more. Like let's say you have a certain amount of battery, like you have a battery that's this size, and you want to maximize how much work you get out of it. Having a more efficient like gear train system will result in a longer use of that, and also will increase the torque performance of your of your reducer. So you'd have because you don't have as much internal friction, which means stuff isn't slowing it down, which means it's easier to spin. Lots of benefits. And then life cycle. this has to do with how many internal components are rubbing together. So, and also like what kind of loads and situation you might have your reducer in. In an example where you might have a bunch of shock loads, having a single tooth of contact might not be great, because if you have a bunch of shocks repeatedly over a single tooth, that could result in a failure of that tooth. Well, if you had a bunch of teeth in contact or different types of like torque transmission features, then you would gain, or it would basically have a longer life cycle, or in shock loads, it would have a longer life cycle. But in purely like rotational loads, like how many times can I rotate this? It might have more parts that are rubbing together, which means that they're kind of wearing down over time. And it's kind of like an engine, you know, when you buy a car, you look for a car that has a certain like mileage on it. You usually don't want to go above like 200,000 miles on a car that you buy, because it wears down, like all the pistons inside the cylinders kind of start wearing out, and like the clearances between them become larger. And the same thing can happen in your transmission, or in this case, gear reduction, which means that your tolerances become less accurate, which is really important to keep tight on a like a system like this, because even the smallest changes in position of the gears or changes in how they're contacting each other could lead to either catastrophic failure or incredibly reduced like performance and efficiency, or could even just like create a lot of backlash, which is something that can't always be corrected for. And backlash is simply just how much play there is in a gear before it comes in contact. Whoops, before it comes in contact with a before it comes in contact with like whatever is actually powering it. And then the last factor to consider for us is complexity of design and complexity to manufacture. This is something we're designing ourselves. So it's something that we should have the capacity to do analysis for. It's also something that we might be manufacturing ourselves. In some cases, you could buy a lot of parts off the shelf and you just have to manufacture the housing that would assemble into it. In other cases, you might have to be manufacturing every component inside the gearbox because of how custom it might have to be. And so those are all the factors that I'd say are important to think about in selecting maybe not all of them, there might be a couple more, but in selecting a system for our exoskeleton if we go with motors. This is the wrong words. I'm missing a slide here. That's great. Oh, it was deleted. Okay. So first is possibly the simplest. This is the same system that we ran on the knee for our first prototype last year. It's called a gear train. And a gear train is what they have in a bunch of like car transmissions. It's very commonly used. It's incredibly straightforward and simple. It's just one gear in contact with another gear that's in contact with another gear, and then you just like link them together in a chain. And what's great about these is that like they've been used so frequently and so widely, is that there's an incredible amount of documentation on how to analyze these. There's calculators for you that'll do it for you. Every single part you could possibly want is available off the shelf, and it's relatively efficient. So in a car where you want to be able to get like the most horsepower out of your engine, you want a system that provides like not a lot of friction. And so having an efficient system is great for that. It also sometimes, depending on how you do it, if you spin them up really fast, can have a whole bunch of inertia. Sometimes that's good for cars if you want like basically like a flywheel to store energy. In our case, that's not what we're really looking for. Some cons with this is that it can be difficult to package. Like I mentioned before, sometimes you need a really large gear and a small, like for gear trains, your gear ratio is just like, if you want 10 input revolutions to 1 output revolution, then you need one gear that's 10 times the size of the other, which can lead to really large gears. And that could also lead to like a heavy system, which wouldn't be great for an exoskeleton. And its torque capacity compared to some of the other like systems that I'll cover in this presentation isn't necessarily that great, because there are only like one or two teeth that are in contact at any given time, which means that like you have to size your gears to be larger, which makes them heavier, which makes it bulkier, blah blah blah. Anyway, planetary gears. This is what we used on our hip gearbox last year. These are great in so many ways. They have a higher torque capacity because you'll notice in these like little animations here, there are a bunch of teeth in contact. It's not just the teeth on the outside of these, like these are called planet gears, contacting this ring gear. It's also the teeth that are in contact with the sun gear from the planet gear. And so there's a bunch of teeth in contact, which means that you're much less likely to shear a tooth off, which means you can size them to be smaller. And on top of that, you can achieve gear reductions in a much more compact space. For example, if this green shaft in this upper animation here, whoops, that green shaft is your input, it'll spin that green gear, the planet gear, which will spin the sun gear. It'll spin the sun gear, which will spin the planet gears around a statically held ring gear, and then your output is achieved in like a relatively small package. And you can also output directly from the ring gear itself. So if you held, like in this animation, this lower one, if you held the planet and sun gears static, then the ring gear will rotate, and that can be your output. And there's actually 6 different ways to achieve a power output from this gearbox. And so it's kind of multifunctional in that way. Let's see, what did I miss anything? High torque capacity. This is not great for high-speed applications. It kind of depends. The reason I would say it's not great for high-speed applications is because there's a lot of surfaces in contact, which means that you're going to have a lot of rubbing, a lot of wear, but it's also heat that you're concerned about. And we don't do anything that would bring these up to crazy high speeds unless they were all the way at the like right next to the gear as our initial reduction. But that's just something you have to be a little like aware of when you're coming to designing it, and make sure that you size it so that it can handle the speeds you're running it at. So that's not really a huge deal. There aren't a whole lot of things that are wrong about the planetary gearboxes. They're kind of great. This is kind of an abstract one. It's more of a novel, like a novel gear reduction method, although it's becoming more widespread, just because of manufacturing capabilities are getting more advanced to the point where this is like more realistic to manufacture properly. And I think this is also something that's feasible for us to manufacture if we were so inclined. This is called a cycloidal drive. And this is the one that achieves the greatest reduction in the smallest package. And there's different ways of structuring it. Like this planetary gearbox can maybe achieve like a reduction of 1 to 10 in this volume, while this can achieve a reduction of like 1 to 40 in the same volume. So that's a considerable distance, especially considering your ratios multiply. So if you had two 1 to 40 gear ratios stacked on top of each other, then you get a 100 to 60 gear ratio. Well, if you had two 10 to 1 gear ratios stacked on top of each other, you'd only get a 100. Wait, did I do that? Yeah, a 100 to 1 gear ratio. Well, in this case, is that, I feel like that number is low. 40 times 40 is 100. Is it 1,600? One sec. Sorry. I haven't done mental math in a minute. Yeah, it's 1,600. So there's a pretty big difference between 1,600 for two of these guys stacked on top of each other and 100 to 1 on this one. So that's just something that's cool about it. It might look a little confusing what's going on here, so I can explain it briefly. Basically, this green shaft here is your input, and it's got a offset like cam that is driving this cycloidal disk, which is generated using the cycloidal equation that you learn in like 3. So it's pretty straightforward to make. And basically by driving it like this, is orthogonally the correct term. By driving it acentric from the center, you basically produce this kind of oscillation that pushes the cycloidal disk off of these pegs on the outside, causing a rotation. And then all these purple pins are your output. I hope that makes sense. It's a little difficult to wrap your head around at first. But once you see how this can be like optimized and packaged, and I have some pictures later, it can become incredibly stupid how crazy gear reductions you can achieve. Also, it's zero backlash, which is something I want to come back to on these. Spur gears backlash is basically like how much space there are between the teeth for them to wiggle back and forth. And with a planetary gearbox, your backlash can be really large because your tolerances stack up throughout all of your gears, and you have a shit ton of them. Same thing with a gear train, but on a cycloidal gearbox, you don't have to have as high of tolerances to achieve like pretty much zero backlash, although you still need crazy high tolerances. And so the trickiest part about this is it hasn't been around for super long, so there isn't a whole bunch of great like easy analysis you can do. There are no calculators that I found that can just like plug and play cycloidal gearbox. Also, we wouldn't be able to do this off the shelf. We'd have to manufacture most of it in-house. I'm a fan, but it might be a smarter move to just go for the planetary gearboxes because it's difficult to have you need people working on this full time, and so it might not be feasible for us. And then this is just an example of a like assembled multi-stage cycloidal gearbox. There's like it's a little more complicated than just a straightforward cycloidal. This is what's called a differential cycloidal gearbox, which basically operates with both internal and external cycloidal discs that rotate relative to each other. And this small package, which could fit in the palm of my hand, is a 1 to 1 billion gear reduction. So 1 billion rotations of this input shaft, or 1 billion rotations of this input shaft result in 1 rotation of the red output. And so you can see how incredibly efficient this packaging can be. Like you could probably lift, I don't know, like the Titanic with this gear reduction until it breaks under the load of the Titanic because its torque capacity wouldn't be high enough at this scale. Anyway, this is one I thought I'd just throw in here. This is just a fun, like if you get into it and you're like, oh wow, there's a lot of really cool like different types of gear reductions out there. And this is also only the back-drivable kind. There's even cooler non-back-drivable ones. But this is called a inception drive. It's another like novel drive idea that's kind of inspired by a CVT. If you're familiar with what's called, it's continuously variable transmission. But this one is a play on the continuously variable transmission, and it actually achieves what you could call a infinitely variable transmission. Like basically what that means is that like with all of these previous like reducers I've shown you before, you have a fixed gear ratio. It's like if you have 10 rotations on the input, it's always going to be 1 rotation on the output if you have a 10 to 1 gear ratio. But with something like this, which is electrically controlled, you can have 10 rotations on the input and then 5 rotations on the output, or 10 rotations on the input. Yeah, it is a crazy cool drive. And what a CVT is basically you have a range of gear ratios. So you can either be like 5 to 1, or you can be like 20 to 1. And so you have that range from between 5 rotations on input to 20 rotations on input to get the same output. And that's what a CVT is. What this is infinite. And so you no longer have those bounds. It's like I can have a a 1-to-1. I can have one rotation input, one rotation output, or I can have like one rotation input and a billion rotation output, or I can have that flipped around entirely. This gear ratio could actually, or this inception drive could actually have like a billion rotations of input and 0 rotations of output. Because it's just like, it's not only that you can like change it within that bound, you can actually go into the negative and start going from a reduction to a speed increase. Anyway, I don't mean to go too deep into that. If you guys have any questions or you'd like me to delve deeper on anything, this would be a good time.
I had a quick question about Backlash.
Sure.
How important are, like, I know the Planetary Drive has probably a lot more backlash, obviously, than the cycloidal. But how important do you think that is with the exoskeleton?
So backlash is something you can actually compensate for through software. So if you can measure how much backlash you have, like let's say you have, this is an incredibly large, absurd number just for the illustration. Let's say you have 2 degrees of backlash, and so you can push the leg like 2 degrees back and forth. So what you can do with your code is while it's being driven by your motor, every time you switch direction, you have the motor travel an extra 2 degrees to compensate for that backlash. Like, because backlash is only comes into effect when you switch directions. If you're always in the driving direction, backlash is effectively non-existent unless you push on the leg from the opposite direction, and at which case you'll have 2 degrees of play. But if you're constantly like switching the leg back and forth and moving it back and forth, you'd have to have like that 2 degree over rotation every time you switch directions, which will compensate for it. And then I'd say the only issue, the really big issue that I'd see with backlash for our application is when you have a back-drivable system, it means that like if you step on a certain location, or if you just like step anywhere that is opposite to your drive direction of your shaft, then your like the exoskeleton will move 2 degrees and that will be uncontrolled. So like there will be a certain amount of play. It'll kind of feel like when you're walking it'll feel like it's wiggling a little bit. But I don't expect that the amount of like the off-the-shelf planetary drives that you can get probably have less backlash than what we would be able to achieve if we made our own cycloidal drive.
Okay.
If that
Do
makes
you
sense.
say that cycloidal drives have no backlash, or that can be achieved?
It can achieve 0 backlash. Depends on how you manufacture it. But it's much easier to achieve 0 backlash on a cycloidal drive than it is on a spur gear system, because it's actually impossible to do it on a spur gear system.
Okay. And then kind of going back to the just overall conversation of making it back drivable, are you like looking at the different, like comparing the planetary to the cycloidal, what are kind of the pros and cons with the back drivable? If that makes, sorry, that question didn't make a lot of sense. Like are both systems able to be back drivable, and how easily are you able to make them back drivable?
So both systems will always be back drivable. You don't have to worry about making that yourself. The things that make them more difficult to drive, like be back drivable, are internal frictions, and so that's efficiency. So if you have a system that's less efficient, it's going to be harder to back drive. Although I wouldn't be worried about that on our scale, because if you have the weight of a person behind it, it's most likely going to back drive. Comparatively, it's hard to say. Something that also contributes as a factor to back drivability is how much inertia a gearbox has, because like to back drive it, you have to accelerate all the gears that are behind it. And so if you have more gears or more like an inertial, like if you have a larger moment overall inside your gearbox, it's going to be harder to back drive. And off the top of my head, I couldn't tell you which system would have a larger moment.
that makes more sense. Thank you.
Yeah, non-back-drivable systems are those which like are literally impossible to push from. Like I can give you an example just to contextualize this. It's like a like a harmonic gearbox would be an example. I wonder if this is what will pop up. Oh, a worm drive. This is perfect, right? So this is a worm drive. It's a super simple type of reduction. And I think we almost used it on the knee last year. I can't move your faces out of the way. There we go. So basically, your input is the worm gear. You rotate the worm gear, which rotates the I think this is called a shell gear. I forget what the lower gear is called. But basically, if you were to try to rotate this larger output gear, it would not be able to turn the worm gear because it just creates an axial load. So when you rotate the worm gear, it creates a radial load on the output gear. But when you rotate the output gear, it only creates an axial load on the worm gear, not a radial load, which means the worm gear will never rotate. Another like less physicsy way like gearbox we can look at would be a harmonic gearbox, which looks like this on the inside. That's small. So it looks like this, and basically you rotate, your input is this green cam that just rotates in a circle, and your output is this red little band. And if you tried to like grab that band and tug on it and turn it around, you're just going to push it into the ring gear. You're going to push it into the teeth. Like there's no way that this, like even if you could rotate that red band, which you can't because it's stuck in the teeth of the ring gear, there's no way you would rotate the cam, which is your green input shaft. Like it would just slide. And so it's impossible to push the output shaft back and rotate the input. And that's what a like non-back-drivable looks like.
Yeah, that's kind of cool looking, like how that works.
Yeah. That's all I had. But yeah, if you guys want like other topics too, it wasn't too bad to put that presentation together, and I can talk about like other stuff.
Awesome. Thank you so much.
Sure.
Okay, how do I recording? Okay, awesome.